All right. Well, happy Monday. Happy ninth week. The end of winter quarter is almost in sight now. So anyway, I hope you guys are doing well. I hope you're I don't know, any group projects and stuff. That's all going good. Okay. On Friday we did like a review of intro stats. And I guess this first part is still a review of intro stats, but we're gonna just start off kind of doing a classical hypothesis test where we compare proportions, and there's a few ways to compare proportions. One is you could do the two proportion z-test, which is what I'm going to do here. You can also do a chi-squared test. That's also possible. And you can also do, that kind of, but anyway, we're going to do a comparison of proportions. We'll do it kind of the classical approach, review of intro stats here, and then we will also do it using, we'll do a randomization test, and I'll show you how that works too. All right, so this is just a simple example. I completely made up these numbers. I have no idea. I don't really know what the true numbers are, and so if you actually know, because whether a student is an international student or not is not something that is not information I get. But anyway, I've just said, okay, in my class, I often have students who are stats majors. I often have students who are data theory majors, and so I just said, I wonder what proportion of students are international students. So let's say I get a random sample of 150 students majoring in statistics, and then we say, are you an international student? We'll say 75 are international students, okay? We get a random sample of 160 students majoring in data theory, and we're gonna say 64 of them are international students. And so we're gonna say, okay, if there's a difference in these proportions, right? Does this data provide evidence that the proportion of international students is different for students majoring in statistics and students majoring in data theory? So this is our thing. Again, made up numbers. And so we're going to compare the proportions of these two samples. And this is what our observed data says. We're going to say, in statistics, we had 75 international students out of 150 students total, and I just did p-hat stats is 0.5, and then for data theory, I did 64 international out of 160, and so 64 out of 160 is 0.4. I wrote p-hat math. I guess I could have wrote p-hat data. It's data theory is not math, but there's certainly more math than regular statistics. I mean, I don't want to get in trouble by my statistics colleagues, but data theory, there's definitely expectation of more theoretic math and stuff. That's the theory part, right? Okay, so anyway, so as far as what we see, 75 out of 150 is 0.5, 64 divided by 160 is 0.4. What's that difference? 0.5 minus 0.4, we get a difference of 0.1. We get a 10 percentage point difference between the two proportions, and the question is that 10 percentage point difference statistically significant, right? So when we set up our null hypothesis is something along the lines of, both of the majors have the same proportion of international students. There's zero difference between the proportion of international students for our two majors. And so our null hypothesis is that p stats minus p math is 0, right? So these p's do not have hats. These are proportions in the population. And so the population of stats majors and the population of math majors who are international students, the difference between them is 0. The alternative is that there is a difference between the proportion of international students, and that difference is not 0. And so P is the proportion of students who are international in either of these cases. And if the null hypothesis were true, when we take a random sample of students, we expect the observed difference between these two proportions to be 0. We ended up with a difference of 0.1, 10 percentage points. And is that difference statistically significant? So is our question. Okay, so I don't know if you remember doing this kind of test in your intro stats course. Here we're going to apply the central limit theorem, and we're going to say the difference between two proportions drawn from random samples, I should say, can be approximated with a normal distribution. And that normal distribution will have a center at 0, because it's, we're drawing two random samples from, basically the same population. And we're saying, hey, what kind of difference would you expect? Well, we expect differences around 0. The standard error is given just by this formula, and you have to do some calculations. We expect anytime we draw two random samples, we expect that difference to be 0, and we do this. So kind of just going through that, we're going to use the results to calculate our p-value. The p-values, if the null hypothesis were true, what's the probability of getting the data that we observed, or something more unusual, right? So what's the probability that two populations that have the same proportion, when you produce random samples, you're going to get a difference of 0.1 or something more extreme. And so our p-value here is, we're going to say, what's the probability that the absolute value between these two proportions is 0.1 or something greater. We're using the absolute value because we're interested if the proportion for stats is higher than the proportion for data theory. We're also interested if the proportion for stats was lower than the proportion for data theory. So either a positive difference of 0.1 or a negative difference of 0.1, or more negative 0.1 or something more negative is interesting to us. And so that's why we're going to use the absolute value there. Okay, you plug your numbers in, you get an overall proportion of 0.4484, you get your test statistic z, you go through the math and you get something around 1.77. And then when you calculate your p-value, right, you get both the positive and the negative side, and you get a p-value of around 7.7%, 0.0768. The illustration is, this is our normal distribution that we're using to approximate our sampling distribution. This is centered at 0, and we observed a difference of 0.1, and we want to know what's the probability of getting a difference of 0.1 or something more positive, also negative 0.1 or something more negative. And so the area is around 3.8% in each of these tails, and when you double that, you get something around 7.7 percentage points. Okay? Now technically, the sampling distribution is not a perfectly normal distribution. We are approximating it with a normal distribution. But if you think about, what kind of proportions can we get? Here we got 75 divided by 150, which is 0.5. But, the only other possible numbers are something like 76 divided by 150. Okay, 76 divided by 150 would be like 0.5067. Or 74 out of 150, which would be like 0.4933. So you only have a certain, there's only discrete values you can get for this p-hat, and there's only discrete values that you can get over here, right? You can either have 65 out of 160 or 63 out of 150 or something like that, right? So you only have certain discrete values, and so only certain proportions are possible, and proportional differences are possible. But we're just saying, there's enough. We're going to approximate it with a normal distribution, and the normal distribution is approximately this thing, and we can do our calculations, and we get a p-value of around 7.7 percentage points, right? P-value of around 0.077. So if our significance level is, say, 5%, then our p-value ends up greater than alpha. We would not reject the null hypothesis. And we say, you know what? I got 50% for stats majors. I got 40% for data theory majors. Okay? The data that we have, that difference of 10 percentage points is not big enough for me to be convinced that it was something other than randomness that produced this difference. Okay? So, 7.7 percentage points is not a p-value of 0.077 is not huge, but it's also not small enough for me to ignore, right? So if the proportion of international students majoring, I should say, in data theory and majoring in statistics is the same, we expect the samples drawn from each population to have the same proportion. The random sampling process can still produce two random samples where there's a difference of 10%. And this happens by random chance with a probability of around 7.68%, okay? Not a large number, but not small enough to completely dismiss it. So this difference of 10 percentage points is, we can't conclusively say it was caused by something other than random chance. So we would not reject the null hypothesis. Okay, and I think that's kind of review, right? Maybe we've forgotten some of the details of this thing, but this process I think is familiar. But I want to just kind of reiterate that using the Z proportion test relies on the central limit theorem. And you learned about the central limit theorem, and one of the conditions is that you need to have a big enough sample, right? Your sample needs to be large enough, and large enough when we're dealing with proportions usually means you have at least 10 yeses and 10 nos. Okay, so whatever thing you're looking at, you need to have at least around 10 yeses and at least 10 nos in both samples, and that's kind of good enough to use the central limit theorem. In our data, we had a sample of 160 where 64 were yes and 96 were no, or sample of 150 where we had 75 yes and 75 no. So all of those numbers were bigger than 10. So using the central limit theorem was okay. But sometimes you will have samples that are not big enough, okay, or other kinds of things going on where you don't want to use the central limit theorem. And so one thing that we can do is use a randomization test, and then on Wednesday I'll also show you the bootstrap test. So that's what we're going to look at today. Today we'll look at the randomization test and look at a situation where it can be used there. All right, let me go ahead and give you your first view quiz answer, which is the letter D. D as in dog is your first view quiz answer, D. Okay, so I'm going to show, we're going to play a little video here. And and this video comes from an old TV show called Mythbusters. I don't know, did any of you ever watch Mythbusters? It was like back, I don't know, I guess started in 2003 or something, and it ran for like 18 seasons, or I don't know, some really long time, but it's been off the air for like several years now. But anyway, in that show, they took some kind of urban legend or some kind of thing, and then they would kind of test it out to see if it was possible. And it was a fun show, and I like the idea of testing things out rather than taking something at face value. But also, some of the math that they did was a little bit shaky. Okay, and so we'll take a look. But anyway, I have to pause the video, pause my recording here, because one time I recorded, part of the episode here, and then I got a copyright strike. So anyway, I'm gonna, if you're watching the video, there's gonna be a pause, and then I will come back and I'll just describe what happened in the video here. But you guys will get to watch. Okay, I think I'm back to recording. Okay, so this is for people watching the video and didn't get to watch. But so in the video, Mythbusters, they wanted to test this hypothesis if yawning was contagious, and so they set up this experiment and they ran it, and they got 50 people to participate, and each participant was told to sit in a small room, and they were monitored for several minutes. And before they entered the room, some of the people saw a person yawn, and they said that's the seed yawn group, and other people did not see anybody yawn, and that's the control group. And then the Mythbusters team then records who ends up yawning and who doesn't yawn. And so they wanted to see, if people who got the seed yawn were more likely to yawn than those people in the control group. Okay, now and the conclusion, they came to the conclusion that yawning is contagious, right? So a couple things to know. The sample of people that were selected to be part of the study was not randomly selected. They went to like a flea market, and then they just got kind of arbitrary people who agreed to join, and then they randomly assigned who's going to get the treatment in terms of the seed yawn and who's going to get control. And that was done a little bit systematically. They said every third person is a control, is going to be a control case, but you can imagine the people who, the order in which they went could be treated as a kind of a random order here. And they didn't show the actual values, but you can kind of figure this out. They said 29%, 25%, and if we go with 1/3 were in the control group, then that means our seed yawn, we had 34 out of 50 were in the seed yawn group, and 10 of those people yawn, and so that's a p-hat of around 29%, 29.4%. And then as far as the control group, we would say 16 participants, 4 of those people yawned, and so our proportion there was 25%. Okay, and I think in the video they said, well, the difference between 29% and 25% is not dramatic, but given that it's their largest sample ever, 50 people, they said, we're convinced that, this confirms the idea that yawning is contagious. Okay, and the narrator says, there's little doubt it does seem to be contagious. I don't know how you feel about a sample size of 50, whether that's big or not. It does illustrate a couple things, and one is that a lot of times when we're in this age of like big data and stuff, having a sample size of 50 doesn't seem very big, but when you actually try to run an experiment in the field or something, it actually represents like a lot of effort and time and energy to just get like 50 observations, right? They had to, I think each person sat in that room for around either 10 to 15 minutes, and they could only do a few, and said it took them 5 hours to collect that data, and then they had to kind of build that truck and build those rooms and stuff. So, it was, and all the people working, it represents, a significant amount of time and energy. But even with a sample size of 50, it's not big enough for use the central limit theorem, right? To use the central limit theorem, we need at least 10 yeses and 10 nos in both samples. And in our control group, we had 16 participants, and only 4 people yawned, right? So we have 4 yeses and 12 nos. So that's not going to be enough for us to run the central limit theorem. Okay. But anyway, I guess before I go on, what do you guys think? 29% versus 25%, does that seem to be statistically significant, or what do you think? It could have been the result of random chance? Maybe. All right, so what we're going to do is we're going to do a randomization test to kind of see what kind of results we can get by randomization. All right, so as far as setting up our hypothesis test here looks very similar to the 2-proportion hypothesis test. The only difference really is that we're not going to use the central limit theorem. We're going to use the computer's ability to generate randomization. So, we have 2 proportions. We have a seed group and a control group, or the treatment group and the control group. And basically, we're going to say, what proportion of people yawned given they were in the seed group versus what proportion yawned given that they were in the control group. And the null hypothesis is that these proportions, or the probabilities that somebody yawns, is the same for both groups, right? Is that this is not contagious, that whether you're in the control group or whether you're in the treatment group, it doesn't affect your probability of yawning, that the probability is going to be the same either way. The alternative is that yawning is contagious, that if you are in the treatment group and you see somebody yawn before you go into the room, you're more likely to yawn, right? So we're going to say probability of being in the seed group is greater, or probability of seed minus probability of control, that difference has to be greater than 0. Okay? And what we observed is we got a difference of around 4%, 0.044. 10 out of 34 is 29.4%. 4 out of 16 is 25%. So we got a difference of around 4.4 percentage points. And so if the null hypothesis were true, we would expect differences of around 0. We observed a difference of 4.4%, and we want to know, is that difference statistically significant? Okay, or could it just be the result of randomness? So, this is what we're going to do, right? So if the null hypothesis were true, what we expect, okay, whether a person yawns or doesn't yawn, is independent or has nothing to do with which group they're in, okay? And so that means any difference we observe, if the null hypothesis were true, any difference that we have observed is just a result of kind of the random assignment, okay? And so another way to think of it, and it's a little bit funny to hear this word destiny here, is that we had 50 people in our data, and out of those 50 people, 14 in total yawned, right? 10 in the seed group, 4 in the control group. So we have a total of 14 people yawning. And we can just think that, out of 50 people, some people were destined to yawn anyway, right? They were just going to yawn, whether they were in the control group, whether they were in the treatment group or the seed group, they were just going to yawn anyway. And it didn't really matter which, what happened. It was just, if they sat in the room, they were just going to yawn anyway. And the idea is that if that were the case, could we just end up where 29% in one group yawn and in the other group only 25% yawn, right? Is it possible that that could have happened just by kind of randomly putting them in there and not whether they saw the seed yawn or were in the control group? And if the null hypothesis were true, we're basically saying randomness alone could produce the difference between proportions of 4.4 percentage points, okay? All right, so that's what we're saying would be the case if the null hypothesis were true. And so what is the p-value? Okay, the p-value is, well, what is the probability of getting that difference of 4.4 percentage points or something more unusual if the null hypothesis were true? So if the null hypothesis were true, what we would expect is we expect our two proportions to be around the same. We would expect a difference of 0. We got a difference of 4.4 percentage points. So if we assumed that that both populations, the seed and the control, have the same proportion of yawners, what is the probability that random assignment would produce a difference of 4.4 percentage points or something more unusual? So rather than relying on the central limit theorem, we are going to use randomization, okay? We're going to simulate what could happen in the sampling distribution when the null hypothesis were true. So the null hypothesis says that the random assignment of treatments is really the only source of variation between our two sample proportions. It didn't have to do with being in the control group or being in the treatment group. It's just the random assignment process. And so in our simulation, we are going to set it up so that 14 out of 50 people are destined to yawn, okay? Okay, and we're just going to say, out of 50 people, 14 people are going to be destined to yawn, and then we're going to just shuffle them up. And I'm going to shuffle up where we put 34 people into group A, 16 people into group B, all right? So we are in control of the shuffling process ourselves, and so we know that just by randomness, some of those yawners are going to end up in group A, some of those yawners are going to end up in group B, and we know the only reason why some people ended up in group A and group B is because we shuffled it up, right? We didn't do any kind of seed, yawn, or control group. We just shuffled these things up and we put some into group A and some into group B. And so if we do observe a difference between group A and group B, we know that difference is because of the random assignment process and no other source of variation. It's just the random assignment process. So we want to see what could happen if the null hypothesis were true and the only source of random is the random assignment process, okay? And so we're going to do that. Now, and then we're going to repeat this a whole bunch of times. Every single time I repeat this, I'm going to calculate the proportion group A that yawn, calculate the proportion group B that yawn, and calculate that difference. And after a whole bunch of iterations, we're going to, if we keep track of them, we'll have the sampling distribution for all of the different proportion differences that we can get where randomization is the only source of variation, right? And then that sampling distribution will tell us whether our observed difference of 4.4 percentage points is unusual or not, okay? So we want to know, in our data, we got a difference of 4.4 percentage points. Is that something that can happen very likely, or is that something that's not that unusual? And so if it turns out that, we did a whole bunch of randomizing, and it's really unusual to get a difference of 4.4 percentage points, then that would suggest that the fact that we did get a difference of 4.4 percentage points indicates that randomization is not the only source of variation, that our null hypothesis is wrong. Something else is going on, and that's why we got a difference of 4.4 percentage points, okay? On the other hand, if we do this randomization process and we find out that, it is not unusual to get a difference of 4.4 percentage points, right? This is a frequent occurrence. Then the fact that we got 4.4 percentage points is not unusual, that it could have been the result of just kind of the random assignment process. So we're trying to distinguish whether our results that we actually observed, it could have been a result of randomizing, or if it's an indication that something else is going on. All right, so we're going to code this up. Now, one thing is that the randomization test relies on this assumption of exchangeability, okay? Exchangeability is the idea that when the null hypothesis is true, all possible permutations of the data are equally likely, okay? And if that's the case, then any permutation of the data is exchangeable with any other permutation of the data. At a practical level, exchangeability applies only when you have an experiment and random assignment of treatments was used in the experiment, right? If there was no random assignment of treatments, then exchangeability doesn't apply, and you should not use a randomization test. So, as far as the Mythbusters experiment goes, it wasn't technically random assignment, but you could imagine the order in which the 50 people lined up is random, and if we were to have done the same experiment, but on some other multiverse timeline or something, the people who've lined up might have been in a different order, and we can just we can say, who ended up in the treatment group and who ended up in the control group is a result of randomness, okay? And that that any other kind of assignment of treatment versus control could have been is exchangeable, or is just as likely as any other random assignment of treatment and control. So here we're going to say exchangeability applies in this scenario. If you have some kind of situation where treatment versus control is not assigned randomly, versus if you have an observational study, then the permutations of the groups are not all going to be equally likely. There could be some kind of relationship between being in one group versus another group, and what kind of outcome it is that you're looking at, and you would not want to use a randomization test. So for that, we'll look at a bootstrap example, and that will be in a later lecture. But for here, we're going to say the order in which people kind of lined up to participate in our experiment is random, and so if people just lined up in a slightly different order, they would have ended up in a slightly different randomized group, and any of these things are just as likely as others. Okay, so let me go ahead and give you your second view quiz answer. Second view quiz answer today is the letter E. E as in elephant. E as in elephant is our second view quiz answer. And this is how we would set up our experiment, okay? So we are gonna set up the kind of what does the world look like if the null hypothesis were true? Because that's what we want to know. We want to say, like, what is possible when the null hypothesis is true? And is the particular data outcome that we have, is that possible under the null hypothesis? So if the null hypothesis were true, we're saying there's 50 people total, 14 of these people are destined to yawn. So I'm going to start by creating this logical vector called yawning. And this logical vector contains 50 values, okay? 14 of those values are true, and 36 of those values are false. And so you can see I've got 10 true, 24 false, 4 true, and 12 false. So for a total of 14 true values and 36 false. But and I've arranged them so that out of the first 34 values kind of represent our treatment group, where we have 10 out of 34 true values, and then in the remaining 16 we have 4 out of 16 that are true. But overall, in the yawning, I've got a vector of 50, and I've got 14 true values, 36 false. Okay, and so here I'm going to say, okay, the first 34 we're going to put in treatment, the remaining 16 are going to be in control, and I'm going to take advantage of R's ability to calculate a proportion based on a logical vector. And we're going to say, what is the mean of treatment? So 10 out of 34 is 29.4%. What is the mean of control? 4 out of 16 is 25%. And so I can get the observed difference, which is going to be 29.4 minus 0.25, and I get an observed difference of 4.4%, right? 0.04411765. So this is my observed difference. And again, this just represents our vector of 50 people where 14 people were destined to yawn. Oops. And then to simulate this randomization process and the random assignment, I'm going to use the function sample. Okay? And I think you're familiar with sample, but sample can be used to do sampling with replacement and without replacement. By default, it samples without replacement, and it will basically just shuffle the entire vector that you have. So here, I wrote shuffle, but I should have written sample, okay? So yawning is that vector of 50 values, and if I do sample on yawning, it's gonna just shuffle all 50 of those values, right? And so 14 of those values are true, and we're just gonna shuffle the order of those 50 values, and those 14 true values are gonna end up in different places in the vector, right? So we're just gonna shuffle those 50 values whenever I call sample. And so here is one result of the sampling shuffling process. Okay, so I'm going to do, I set a seed and I shuffle that vector yawning. Okay, and so that order of 50 is just completely randomized now. And now I'm going to put the first 34 into group A and the remaining 16 into group B. So who ends up in group A is completely random. Who ends up in group B is completely random. And there's no rhyme or reason why one person is more or less likely to end up in group A. It's just any possible permutation is just as likely. So who ends up in group A is completely a result of randomness, has nothing to do with treatment or control. It's just who ends up in group A is random, who ends up in group B is random. And then I say, okay, if 14 people were destined to yawn, what proportion in group A ended up yawning? We get 29.4%. And then I say, okay, and what proportion in group B ended up yawning? And I get 25%. So I end up getting like the same results that happened in Mythbusters. So I get, when I say what's the difference between these two things, I get a difference of 4.4%. That's the same results that we got in Mythbusters. That happened by just kind of randomness here. Maybe that's just a coincidence. So let's try it again, okay? So here I just do another different seed and I sample yawning. I just shuffle this up again, and I'm gonna just put, again, 34 people into group A and the remaining 16 into group B. So again, who ends up in group A and who ends up in group B is just a result of this random shuffling process. In group A, I get 23.5%, and in group B, I get 37.5%. So the difference between this and this ends up being negative 13.9%, okay, or almost negative 14 percentage points, right? So by randomness, we get a difference of negative 14%. And so, I want to kind of just see, well, what could happen just by randomness? So I'm going to repeat this process like a bunch of times, and here I'm going to do it 10,000 times. So, so I create a vector to store all of the results of the 10,000 different shufflings. All right, and so I'm going to create a vector called differences. I set a seed outside the loop, right? We don't want to set seeds inside the loop. And then so basically I say for I in 1 through 10,000, sequence along differences is going to be 1 through 10,000. And for each iteration, what do? I take that vector of 50 and I shuffle it. Okay, I do sample yawning. So randomized is just a shuffled group of 50. Basically, I'm like shuffling my cards here. I'm going to put the first 34 into group A. So who ends up in group A is random. I put the remaining 16 into group B. So who ends up in group B is also random. And then we're going to just say calculate the proportion in group A that yawn, calculate the proportion in group B that yawn, take the difference between those, and write that down in differences box I, right? Differences sub I. And I do this 10,000 times. So the computer runs through this 10,000 iterations. And what do I get? For the mean, I get a difference very close to 0, which is what the null hypothesis states, something very close to 0, 0.00198. So I get something close to 0. So that's good. That's in alignment with what I would expect. My median difference is 0.044. Okay, that's interesting. And then, I get differences, as negative as negative 0.599. I get differences as great as positive 0.411. But let's see, what kind of things could happen here, okay? So what was the observed difference that I got in my data? My observed difference was 0.044, positive 4.4 percentage points. And we want to know, okay, how often do we get a difference of 4.4 percentage points or something, more unusual if the null hypothesis were true, right? What's the probability that this randomization process, which is what would happen if the null hypothesis were true, how often did that produce a difference of 0.44 or more, right? Our alternative is that it's greater than 0, so we're only going to be interested in seeing 0.044 or something more positive. Sorry, this should say greater than or equal to, right? So if you're fixing your notes, this should say greater than or equal to. And so I'm going to do the differences greater than or equal to our observed difference. And how often did that happen? That happened over 50% of the time. So my p-value is over 0.5. Okay, so I get a p-value of 50%. So that's a very big p-value, right? So it says this randomization process, right? Because all I did was I just shuffled yawning and I put some into group A and some into group B. This says we get a difference of 0.044 or something bigger that happens over 50% of the time. And so the fact that that's what Mythbusters got is not really convincing that yawning is contagious, because we could have gotten this difference just as easily, with a coin flip, even if yawning is not contagious. Okay, so as far as I'm concerned, this data does not give us a reason to believe that the data we observed, or that the data that Mythbusters observed, was caused by something other than the randomization process, the random assignment there, okay? And so we would not reject the null hypothesis, right? The data we have does not provide reason to believe that getting a seed yawn makes a person more likely to yawn. This data could have easily been the result of just the random assignment and nothing else, all right? So we cannot conclusively say that yawning, we also can't say that yawning is not contagious, all right? It is possible that yawning is contagious and we just didn't collect enough data, or something else is going on. But it's just, the data that we have, 50 people, 50 people observed, 14 people end up yawning, and it turns out that, 10 in the treatment group yawned and 4 in the control group yawned. That could have been the result of just randomness, right? So So we would not reject the null hypothesis. And that's how we would do the randomization test. We don't rely on the central limit theorem. We just kind of produce the distribution by doing the randomization ourselves. Okay. If we had a two-sided alternative, right? If the question wasn't, is yawning contagious and make somebody more likely to yawn, but if it was just like, does seeing someone yawn have any effect, positive or negative, on the person yawning? Okay, it would be interesting to us to see if you see someone yawn, it makes you more likely to yawn, and if you see someone yawn, it makes you less likely to yawn. That would be also interesting to us. So here we would use the absolute value, and again, this would be greater than or equal to. So our p-value here would be the absolute value of this, these proportion differences, is that being greater than or equal to 0.44. And if you do that, you get a p-value of 1, okay, 100%. And that feels really unusual. You're like, how can you get a p-value of 1, okay? And I kind of want to illustrate this just by looking at the values, right? So, the proportion we got was doing 10 out of 34 minus 4 out of 16, right? We got this difference of 4.4% percentage points. And if we just say we have a total of 50 people, 34 in group A, 16 in group B, and 14 people are destined to yawn, what are the other kind of splits that we could have, okay? So I could do 9 out of 34 minus 5 out of 16, okay? And if I do that, I get negative 0.0477, okay? I could also have 8 out of 34, minus 6 out of 16, right? So we have a total of 14 people yawning, so I could do a 8-6 split, and I would get negative 0.139, or, I could do 7 out of 34 and 5 out of 16, and I get, I'm sorry, not that one, ignore that one, 7 and 7, okay? And I would get negative 0.2316, okay? Okay, on the other hand, I could go, if the other direction is 11, and I could have 11 and 3, if 14 people, or 12 and 2, okay? And I get 0.227. So the difference is, if you look at these, if I keep going in this direction, our differences just become more and more negative. And if I go in the other direction, 12 and 2, 13 and 1, or 14 and 0, the differences get more and more positive, right? And what is the smallest possible difference that I can have, right? Because we can only either have 10 and 4 or 9 and 5 or something like that. The smallest possible difference I can get is 0.044, okay? There's no value that produces a difference of less than 0.044, right? The next closest thing is negative 0.047, and anything else just the difference gets more and more extreme. Negative 0.139, negative 0.231, or if I go in the other direction, positive 0.136, positive 0.227, and they're just going to get more and more positive. So it is literally impossible to get a difference any smaller than 4 percentage points with our data. With 50 people and 14 people in total yawning, if you're going to split them into two groups, 34 and 16, which is what they did, you cannot get a difference that's any smaller than 4.4%. So yeah, it's not very convincing, okay? Again, maybe yawning is contagious, but based on this data, we are not convinced. All right, let me go ahead and give you your last view quiz answer, which is the letter C. C as in cat. C as in cat is your third view quiz answer for today. And we'll go ahead and wrap up here. Have a great rest of your day, and we will see you on Wednesday.